Alright, welcome guys. In this video, I'm going to show you how to install and use EasyCFD. So right now we are on its GitHub page, and the link is in the description below so you can start following right along with me. Right here in the README file, there's a brief little description of what this project is about. So, EasyCFD is an automated open source workflow for computational fluid dynamics, CFD, simulations. The goal of this project is to shatter the status quo in education and industry that CFD software is difficult and expensive to use. EasyCFD makes OpenFOAM, an open source CFD software package with a notoriously steep learning curve, easy and accessible by maximizing work done by the computer and minimizing work done by the human user without sacrificing accuracy. Which sounds pretty great if you ask me. This page contains the following. We got some Python code. In this folder we just got a bunch of scripts that make up this program, this graphics window that you interact with to build the OpenFOAM case. We got a sample geometry folder, and here there's some STL files that you can use right off the bat instead of making your own through SolidWorks or FreeCAD or something like that. And we have a necessary software folder, and here we have some installers for some things that we need to use EasyCFD. We need ngrid, you need Python 3, and we also need blueCFD core. Now, this guy right here, the installer was actually too big to be uploaded to GitHub, so you got to follow this link instead. There's also an instruction manual that you can refer to in the future instead of watching this tutorial video over and over again. And now that we've covered everything on this page, I think we can get started with installation. So the first thing that we're going to want to do is just download this entire repository. So we can just do that by going to clone or download right here and download zip. So it's right over there. Just click that when it's all done and good. And extract all. I'm just going to do it in my downloads folder, but you can do it wherever place you want. So just extract, and there we have it. So just let's enter that, and we can start installing our necessary software. So we got ngrid over here. Thankfully, ngrid is a pretty lightweight and small software, so this shouldn't take long at all. Alright, finish. Next up is Python. So you're just going to want to install now. Python takes a little bit longer, I suppose, but not too long. blueCFD core actually can take a very, very long time. So what I'm actually going to do is when I start the installation, I'm going to pause recording and then return when it's all done and good, so you guys don't have to watch 10 minutes of a loading bar. Alright, so we can just close that, and then we can get started with blueCFD core. So like I said earlier, blueCFD core, the installer for it, was too big to be uploaded to GitHub, so you just gotta follow this link instead, which is given in the description below. So you can just go here and choose the latest version. At the time of recording, it's 2017-2, so you're just going to want to click that. I actually have this already downloaded. Where are you? There you go. All right. So we can just get started there. Come on. There you go. All right. Next. I accept the agreement. Next. Full installation. Next. Yeah, you're just going to want to leave all of these checked unless you really don't like desktop icons. Next, and install. Alright, so this is going to take some time, so I'm just going to cut out of here, and then I'll be back when it's all done. Alright, I'm back. The installation isn't done yet, but just a heads up, you may get this message right here. It's not really a big deal. It says MS Microsoft MPI installation failed with error code 50. A version of MPI that is the same or newer is already installed. I highly doubt that if this is your first time installing this that you would get this message, and even if you do get it, it's not a big deal. I'm only getting this message probably because I already had blueCFD on my computer, and I uninstalled it so I can walk you guys through it, and I guess it didn't uninstall this MPI as well. So if you get this, just click OK, and if you don't, it's no big deal. Alright, I'm cutting out again. Alright, we're all set. blueCFD core is all good. Alright, so just uncheck any of these boxes unless you really feel strongly about following them on LinkedIn or anything like that. So just click finish. And right now I guess we can just do a quick test to make sure that everything installed properly. So I'm just going to open up ngrid real quick to make sure. So you should see something like this when you open ngrid up. A quick Python test. You can go to our downloaded repository, go into Python code, and click EasyFOAM. We see this graphics window showing up, so that's a very good sign. So I'll take that as a pass. And just to check our blueCFD core, just right-click a folder, like any folder, and select Open in blueCFD Core Terminal 2017. It's just going to spit out a bunch of messages here, and then here we go. OpenFOAM 5. Alright, so we have everything we need to start using EasyCFD. The first stage in this workflow is geometry preparation through ngrid. What exactly geometry preparation means, I'll explain as we go along. So we're just going to open this bad boy up, and we're going to use the sample geometry files that we downloaded earlier. So just go to import, STL, make sure you're in the right place, and we're going to get started with the damper file. We're going to use the default tolerance of 1e to the minus 10 and click OK. And you should see something like this. You can rotate it by holding down the left mouse button, mousing around, zoom in and out by using the mouse wheel, and you can drag it around by holding down the mouse wheel and mousing around. Alright, so defining boundary conditions. This is what I mean by geometry preparation. So boundary conditions, if you're unfamiliar with them in CFD applications, I guess, they are like regions of the geometry that interact with flow in various ways. And in most cases, they consist of inlets, outlets, and walls. So inlets, like take for example this guy right here. Inlets are where you can have flow enter, while outlets, this guy right here for this case, is where you have flow exit, and everything else is where flow can hit and encounter, like the walls of a tunnel or an airfoil. Let's get started by setting these guys. So you're going to mouse over your desired boundary, press the P key, and then press S key. Alright, so we got feature angle 45 degrees. Since the inlet is a flat face, this isn't really too much of a big deal. This can be like 1 degree because it's really flat, but if we were like using a more rounded or angular boundary, it would need a higher feature angle. In some cases, your feature angle may be too small and not select every face for the same boundary that you want, but this can be fixed by just using the same boundary code. And boundary codes right here is how ngrid differentiates between different boundaries. So for our first boundary condition that we're defining, we're just going to use 1, and for the next different one, we're just going to use 2, and so on and so forth. And like I said earlier, if your feature angle turns out to be too low and it doesn't select like the entire thing that you want, just do it again and just set the boundary code the same. It will like add it to the same boundary. So since this is the first one, we're just going to use 1, and then we're going to process all cells, even invisible ones, click OK, and we can see that our inlet has been selected. We're going to press the E key, E for edit boundary conditions, and we're going to see right here that this BC index, this is the value that we just gave, 1. It corresponds to this guy right here. So since this is our inlet for a BC name, we're going to get rid of BC1 and just give it something that has inlet in it. It can be something like box inlet or inlet 1. As long as it has the characters that make up inlet, it will recognize it as inlet, and it will, and outlet, it's the same thing. Alright, so we're good with that. You might be asking what this guy is right here, this 999999 stuff. This is actually the rest of the geometry that hasn't been selected yet. So this is going to come in handy later. We're going to come back to this guy in a few minutes. So just click OK. And we're going to move on to our outlet. Just do the same thing. Press the P key and the S key. Since this is a different boundary, we're going to use 2. And click OK. Press the E key and call it outlet. Like I said earlier, you can call this like outlet 2 or left outlet or something out like that. As long as it has outlet in the name, you're good. Click OK. And now we're left with is the wall. And this is actually really nice because we can just call this guy wall. You can actually call this guy anything you want as long as it just doesn't have the name inlet or outlet in it. But for simplicity's sake, we can just call this wall. Click OK. And that's pretty much it. All that's left to do is to export this guy as SU2. Important, SU2. Just click Save. And there we go. The damper geometry has successfully been prepared, and we're actually going to go back and do the same for the remaining cases. So let's just close out of that just to make sure that we have a clean session. Open it up again, import STL, and we're going to move on to the foil 0 degrees case. So just open this guy up, same as before. And this file actually is meant to be used for an external flow simulation. And for most external flow simulations, when you're preparing these guys in ngrid, all you have to do is just press the E key and call this and just rename the BC name to wall or anything like foil, wingtip. But I like to keep things simple and just call it wall. And since there's like making sure, yeah, because there's no inlets or outlets here, you just have the geometry of interest, and that's usually included in the wall boundary condition. So just export that as SU2, and now this guy is prepared as well. We're going to close out of this guy again and open it up just to be sure, and just, just for a little bit more practice, we're going to go with a test guy. This is like the damper geometry in internal flow case. So it's very similar to that one, but it's got something a little different just to make things a bit more interesting. Like before, just going to press P, S, call that guy 1. So that's our inlet. Okay. PS, press the E key, outlet. Okay, now actually, this guy right here has like a little bit of an obstruction in the middle of it. So usually, like in a case like this, you would have like water or air blowing through this, and you've got this little obstacle in the way. Now, this is where, like I said earlier, hold on, let's just mouse over this guy and press the P key, and press the S key. Now, this is what I was talking about earlier with the whole feature angle stuff. So this guy, it's not a completely flat feature. It's like, well, It was round when I drew it up in FreeCAD, but you know, it's a little jaggy now. But let's just give this guy a value of 3, press OK, and see what happens. So it didn't select everything. It actually left this one face, just one face left. Come on. But it's really no big deal. Just press the P key again, press the S key again, and just keep it as the same boundary code. Leave it as 3. And now it belongs in the same boundary. Like there's not another thing besides the rest of the geometry. So we're actually going to call this guy refine. And the way my EasyCFD, the Python tool that I code up is set up, is that when it sees the characters that make up refine in a boundary, it actually meshes that region much more like a smoother, I guess. And that comes in very nicely when you have something that's rounded or a region of interest, because as you saw earlier, that was meant to be like a smooth round sphere. It was not smooth at all. It was pretty jagged. So for stuff like that, I recommend using the refine name. And like as long as it has the characters, like it can be like refine 2 or refine ball or something like that. As long as it has refine, you're good. And as always, last step, just give the wall name to the last row. Always leave this guy last. It'll make your life much easier. So click OK and export as SU2. And we're all set for our geometry preparation for the different cases. So we can close out of NGrid and move on to the next stage. And said stage is case construction through EasyFOAM. So you're just going to go to where we downloaded everything in the beginning, go to Python code and EasyFOAM. So you're going to see a graphics window, a Python graphics window, along with a Python terminal. Don't close this guy. If you do, EasyFOAM will close too. Plus, when you want to build a multi-phase simulation, this terminal is used for further input. I made this guy to be as simple, straightforward, and easy to follow as possible, at least in my opinion, but we're going to walk through this together. Answer all the questions below and select build case for fast simulation setup. Well, that's the hope at least. Alright, select simulation destination. Click browse, and we are able to choose where we want our simulation to go. So I guess for us, we can just put it where everything else is for EasyCFD. We can like make a new folder. We're gonna do the damper case first, so we can like call it like damper test, and we can select that. Select the SU2 geometry file. We got to make sure we're in the right place. Downloads. All right, there we go. Damper. Next, specify inlet flow rate and units. For this case, we can do, I guess, 5 meters per second as a flow rate. So we're just going to enter 5. Make sure you hit enter and select meters per second. There's also a cubic meters per second for a volumetric flow rate, if you so want to do that. Next, we got specify flow type. We got air steady, where you just blow air, water steady, where you're just blowing water, and multi-phase, where you can like blow water bubbles. You can like fill something that's initially empty with air with water, or drain something that was filled with water and just blow air to drain it, purge it, I guess. But for this, we're just going to use air steady. Next, we can enter the number of processor cores that we wish to use. If you specify more than 1, then OpenFOAM will run in parallel, and this can speed up your simulation speed. And to check how many cores that your machine has, if you're not sure, you can just check the Performance tab in your Task Manager, which can be opened through Control-Alt-Delete. I'd show you, but it would mess up my recording. It would look really messy. So I'm just going to enter 5. Like I said, if I enter 1, like that's fine. But if you know how many cores you use, you should max out on that to get the best simulation speed. So click enter. Is the flow internal or external? This guy is internal, so select that. Enter the desired angle of attack ranging from negative 30 degrees to positive 30 degrees. This guy is really meant more for external flow, like the wingtip. But I also left this option for internal, I guess, if you wanted to do something like that. But I'm just going to leave it as 0, so hit enter. Is the flow laminar or turbulent? For beginners, I guess, it's easier. It's much less likely for something to go wrong if you just keep it simple. So let's just go with laminar. If you choose turbulent, the K epsilon turbulence model will be implemented. So all that's left to do is just build the OpenFOAM case, and you get this message that says process complete. And let's see, let's just check real quick. Damper test. And there we go, test clean. That's the name of the simulation of the, freshly born simulation. All right, perfect. Now we are ready to make some final touches and run our simulation. So we are just going to right click on our test clean and open in blueCFD. Now you should see this terminal here. It should look like something like this. If some messages like run across the screen at the top here as it like loads, you should close it and open this again. Because like I've had some experience in the past where if you have like blueCFD run for the first time and you try and run a simulation, some things don't work for some reason, but if you just close it and run it again, it works fine. So just keep that in mind. So what we're going to do here is just enter this command exactly, just prep /just prep, press enter. And then this is like a little reminder that I tell the user, but I'm going to tell you this later, so we can just close this and then right click and open test ran in blueCFD. Because what just happened was that the contents of test clean were put in a new folder, test ran, and now the case preparation and simulation is taking place in this directory. So now we're going to enter parafoam. And parafoam is like the command to open a case up in ParaView, which is the post processor or visualizer for OpenFOAM, so you can see what's going on. So we're going to hit apply. And right here we see our block mesh, or like our flow domain. Inside this block is where all the stuff happens. So now what we're going to do is go and open our STL files for our boundary conditions. And you can do that by clicking File, Open, going into Constant, try Surface. And here we can see the STLs for the boundary conditions that we defined earlier in nGrid. We see inlet, outlet, and wall. So we're just going to open all of these, click Apply. Now for this case, everything is inside the block mesh. In fact, well, for any case, it's all going to be inside this block mesh. But if you want to see it, one way you can do it is either click this button here, this little eye button, so you can make the block mesh invisible, or you can decrease the opacity so you can make it more see-through. Right now we can just leave it as a like see-through kind of thing. Now what we're gonna do is that even though earlier when we were using EasyFOAM we specified whether the flow is internal or external, now what that really did was that since it's internal, the block mesh is just large enough to contain the STLs, because everything of interest is inside this STL and contained by the STL. Whereas if it was an external flow case, which we're going to do later, the block mesh is much bigger. It's so it can act as like a proper wind tunnel, so there's enough space for flow to act properly and stuff like that. So with the wingtip geometry that we saw earlier in nGrid, this box here would be much bigger. So what we got to do here in ParaView is tell OpenFOAM whether it's internal or external. So what I mean by that is the flow going to go like, is the flow inside this thing, or is it going to flow around this thing? And we're going to do this by using, well, first I'm going to decrease the opacity of the wall here too. So there we can see what's going on inside. So what we're going to do is go to Sources and go to Sphere. And we can just hit Apply. Now, here we have a sphere, and what we want to do is move this sphere. I'm going to make this guy a little smaller right here. There we go. That's a good size. And what I want to do is move this sphere so that it's in a place of empty space, but inside both this block mesh and this STL area. So what I can do is like say, let's make this 0.2 and see what happens. Perfect. So the coordinates of 0.2, 0, and 0, make sure you keep that in mind, or whatever coordinates that you set. Keep that in mind because this sphere right here, it's not touching anything, and it's in the right place. It's internal and it's inside our geometry. So what we're going to do is go into our system folder and go into our Snappy Hex Mesh Dictionary. So what we're going to do is, you see location in mesh right here. You're going to copy the coordinates right here into this file. So 0.2, 0, and 0. You're going to click Save, close that. We can close this too. And then we can enter this command, snap solve. And all we have to do is just wait for things to run. What's going on right now is that OpenFOAM is meshing the geometry, and I guess in layman terms that means it's converting the STL geometry, the STL files that we have, into OpenFOAM format, so that when it's running the simulation, it's recognizing it as, hey, this is the inlet, this is the outlet, this is the walls, and this is how our simulation is going to behave around that. So it's running in the background right now. That's going to take a couple of minutes, and once that is done, it's going to actually start running the simulation. So let's see, what can I pull up to keep you occupied? Let's see, videos, so let's see what's going on. Downloads, where were we? Damper test, yeah, that's right. Test ran. And here you can see this is where the different processors come into play. Processor 0, processor 1, all the way to processor 4, totaling 5 processors. And in each one, like the computer's divvying up computational power among each processor. Okay, here we go. So you can see on this terminal, there we go, just doing some things. Now the actual simulation is running. So you see the different time steps going on right here. So this simulation, I believe, is defined to run for 200 time steps. So we're like 10% there. This is for like an error steady case, and for different geometries or different types of simulations, like say a multi-phase simulation, you want something like that to run for much, much longer. So just giving you a little bit of background like an insider's view of what's going on. Let's see, what else can I talk about here? You got some different log files right here, so you can see what computer is saying in the background. Okay, here are the functions that you guys used. So you can see here you're copying the test clean to the test ran, and you're running these commands. Right here is the message that you see. And then here is snap solve, the command we just ran. So here we see decompose par. That's the command that tells the computer to break it up into different processors. Then this is the command to run this tool called snappy hex mesh with those different processors. This is what turns the STLs into OpenFOAM format. Here we bring those results together. We like combine them so that it's not deconstructed. We put them together. Then we do it again, but for the actual flow simulation. And then we put those together and clean up the case by removing the processor folders, as you can see here. So the simulation is now done, and now we can see our results. So we can go into Parafoam, click apply, and hey, here we go. This is our first OpenFOAM simulation. So what we're seeing right now is the pressure distribution of this case. So let me see. Let me just see something real quick. Just making sure. So right here you can choose which parts of the mesh show up. So yeah, as I thought, this is the inlet. Makes sense because that's where like the high pressure area is. Okay, so that's pressure. What is okay? So we see pressure. Now we can see. What's a good way? Okay, we can use the slice filter to get a cool picture of our velocity profile. So let's see. Slice 1. What's this? X normal, we don't want that. Y normal, yes, that's what we want. So just click apply. Now this is still pressure, but you just go up here. You, instead of P, you go to U. Use the one with the dots, not the cubes, because the ones with the dots, these are interpolated and give you a cleaner picture. Like, let's see what happens. Yeah, so if you use the cubes, you can see it's more like grainy and stuff like that. I guess it's technically more accurate, but it doesn't look as nice. So let's just see. Okay, let's go to U. There we go. Beautiful. Beautiful. Isn't that so cool? Like, oops. There we go. Isn't this is just so cool. Like, you can see the flow just come in and just whoosh, and you got these like all this stuff going on right behind it. That's so cool. All right. So good job, guys. You just did your first OpenFOAM simulation. Well, there's so much left for us that we can do, but now you guys kind of have a basic understanding of how to run an OpenFOAM simulation. Let's see. I guess what we can now do is do the same thing, but with the wingtip case. So we can just close this guy, go back to our thing right here, EasyFOAM, and I can show you what an external case would be. It's really going to be really similar, plus I can show you just how fast this thing can be, instead of me just telling you guys what to do at every step. Wingtip test, we're going to choose that guy right there. That's not the right one. let's just do 5 meters per second, I guess. I'm pretty sure I actually have 8 cores, so let's just do that. It's going to be external, and let's change it up a bit. Let's go with 10. And let's go with laminar. Build open film case, process complete. All right. So, wingtip test. All right. So you can see right here, this is just it rotating the thing by 10 degrees. Okay. And we can close this. Then we're going to open this guy in ParaView. Hit apply. All right. So let's just, as before, open our STL. Since it's just the wall, we just have that. And we're going to decrease the opacity. As I said earlier, since it's an external flow case, this block mesh, our flow domain, is going to be much, much bigger. Since this case over here, it doesn't have its own inlet, outlet, and stuff like that. And also, as we can see, wait, that's not the right one. Come on. There we go. And as you can see, it's tilted a little bit. That's where the command for the angle of attack came into play. So now what we're going to do is sources, sphere. Let's see what happens here. Okay, that's pretty big. Let's go 0.5. Okay, now let's just say 0.1 or something like that. And that works. So what we're going to do is, just as before, go into our snappy hex mesh, use those coordinates, 0.1, 0, 0, save. Now we can close all that and just do snap solve. And that's pretty much all you need to do. The computer does the rest of the work, and that's what's really nice about this tool. Without a tool like this, there's just so much more time and effort for the human user to put in. While this thing is doing its own thing, you can do a bunch of other, you can just do other things. I don't know, like get a coffee or watch some YouTube videos or go on Reddit or something like that. So what I'm actually going to do is just stop recording for a little bit, and then when the simulation is actually finished, I'll pop right back in. Alright, I'm back for the third or fourth time. As you can see from my different parafoam commands here, I messed up on these past takes. So our wingtip simulation finished running, so we're just going to enter parafoam. I'm going to be doing it for the fourth time. So we're just going to hit apply. Here we see our block mesh. It's all green. We don't really care about that. We care about the wingtip. So what we can do is go right here, check the wall, and uncheck this, so we can just see our wingtip in its singular glory. You can see high pressure area where the incoming flow hits the wingtip. Really cool stuff. All right. One thing let's see what else I can show you. Let's go back to the internal mesh. There we go. Let's see. Let's get another velocity profile of this guy. So just want to make sure that it's going in the right way. Okay, so we want something like that going across that way. Okay. So just go to the slice filter and what was that? X, Y, we don't want Y, we want Z. Okay, there we go. So just hit apply, and there we go. So we see pressure, but we want velocity, so do that. There we go. You see that? Let's see what happens if we, because this is like at the center of the wingtip, not where the actual thing, not the actual tip where it splits off. Let's see what happens if we can. There we go. Yes, yes, there we go. Just a little bit further, I think. That should do it, I think. There we go. There we go. And you can see the, like the streamlines, the, like just it passing at the trail. Alright. One more thing we can do with this guy, I guess. So, okay, slice, we can get rid of this guy. One more thing we can do is, get some streamlines. So we're just going to use the stream tracer tool right here. Click this guy. We don't want... Okay, let's get inside this guy first. Alright, I don't think we want this line right here. We should... It says high resolution line source. I think a point source would be much better. We can move this guy around. We can change the size of it. We can like change this to like 0.05. There we go. And let's see, move this guy over here, where we care about the flow more, I guess. So, okay. And yeah, all right. I think we're good. Just hit apply. There it is. There it is. Change this to U. All right. And can we? There we go. There we go. So you can see the flow coming in all nice and straight. And it sees this guy, screws everything up. You can see things twisting and turning right over here. Just so cool. Just so cool. Just like it vortexing and stuff like that. Alright. So, today, together guys, we just did our first OpenFOAM simulations. This has been a pretty basic introduction with the stuff that you can do with OpenFOAM and the EasyCFD workflow, but in future videos, in more advanced topics, I guess, we can delve more into multi-phase simulations and dabble with turbulence. Thank you for joining me. It's been a lot of fun, and I hope you found this fun and easy to follow too. Peace out, guys.